Hello, Science 10s. Welcome back to another lecture in our chemistry unit. So today we're going to be looking at pages about 65 to 71 in your note package, and this deals with something known as the mole. Okay, so we're going to bring in a little bit of math today. And being able to do this stuff, it really kind of goes back to whether you can write a chemical formula. Okay, make sure you know all the rules of writing chemical formulas, put those formulas together into a chemical equation, and then being able to balance those equations. Okay, so if you haven't looked at balancing equations yet, if you haven't looked at writing chemical formulas and predicting the products of chemical reactions, you need to go back and look at those lectures, and you need to do that homework. Okay, I've said it before in class, and I'll keep repeating it. With chemistry, and later on we're going to be doing our physics unit with physics. It's all about practice, 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 practice. Okay, now I'm going to be doing chemistry and physics because for those of you who are going to be taking chemistry and physics later on at the 20 level, you're going to need a lot of these skills. Okay, so your Chem 20 teachers are going to assume you know how to balance a chemical equation, you know how to write a chemical formula. Okay, and today's material, I'm going to be kind of assuming the same stuff. So if you haven't done that homework, go back, do it. Okay, now if you're having trouble with balancing equations, which a lot of people do, if we were back at school, PDTs would be filled with students asking about balancing chemical equations. So if you're having problems, please, you need to contact me. Okay, so the best way to do that is through email. Let me know, you know what, I'm having problems with this question or that question, and I can even, tape record a session and put it up on the Google Classroom because many people will probably be having the same question. Okay, so now hopefully you understand how to balance an equation, you understand how to write a chemical formula. Today what we're going to be dealing with is something known as the mole. Okay, now what is the mole? Well, we'll get to that in a second, but first thing I want you guys to understand is that, whether it's physics or chemistry or biology or whatever science, we want to measure things. Okay, we work in a laboratory with things, and it's much easier if we can measure what we're dealing with. Okay, now being able to count the number of things. Now, again, I come from a biology background and I come from an ecology background. So if we wanted to study the health of a particular river, we would go out and we would catch bugs and we'd count them. Okay, or we would electrocute fish and we would count them. Don't worry, the fish weren't dead. It was almost like tasering them, right? So we could count them. They'd float to the top. We'd net them. We'd count them. We'd let them go, right? So counting things is kind of one of the most fundamental skills that we have in any science. Now, in chemistry, we're dealing with atoms. So how the heck do you count atoms, right? So for example, maybe you're holding a pencil right now. Okay, there's a pencil right here. Here's the lead of the pencil. How many atoms are in that pencil lead? Right? Well, that seems like it's an impossible task. How can you possibly count the number of atoms inside of a pencil lead? And really, you can't. Okay, for the most part, atoms are there. You can't see them, right? Even with the most powerful microscopes, you can't see them. So it's kind of almost impossible to physically count things that you can't see. So we use kind of an indirect method when we're counting. So again, atoms are very, very small, and it takes an incredibly huge number of these atoms to make up any visible amount of a substance. Okay, so when we're looking at a pencil lead, it's not just one or two atoms in there. It's geez, I don't even know the number, quadrillions, quintillions. I don't even know the name of a number big enough, a number of atoms to make up that little bit of graphite in that pencil lead. Pencils aren't lead, by the way; they're carbon, right? Put together in something known as graphite. So again, here's a glass of water, right? That glass of water is made up of molecules, not atoms, but well, I guess indirectly it's made of atoms, but it's made of H2O molecules. Could you count the number of H2O molecules inside that glass of water? And the answer is no. Okay, but we can do it in an indirect way by looking at the mass of that substance. And by using a little bit of math, we can translate that math into the number of atoms. Okay, if we know how much one atom weighs, then we can figure out, if we have this much mass, how many atoms are in there, okay? Now, again, counting individual atoms is ridiculous because it takes so many atoms to just make up a very small amount of some substances. So instead, we count groups of atoms, okay? Now, again, this can be confusing, um, but you guys are already counting groups. So when you talk about a pair of shoes, you know that a pair of shoes is two shoes, okay? When we talk about a dozen of anything, a dozen eggs, we know that a dozen is 12. Okay. So I don't need to tell you, I don't need to say, oh, there's 12 eggs in that cart um, or carton. I just say, oh, there's a dozen, and you know that that's 12. Okay. A flat of pop, a flat of, beverages, there's 24. Okay. That's just a known number, right? So a pair is two, a dozen is 12, a flat is 24. So these are some words we use to group objects together. Okay. Now in chemistry, we also have a word for a group of atoms. So in chemistry, we have a number called a mole, and a mole is like a dozen is 12, and a pair is two, and a flat is 24. A mole is 602 with 21 zeros. Okay. So a lot of times what we say is it's 6.02 times 10 to the 23rd atoms. Okay, that's a huge number, and it doesn't have to be atoms. We could have a mole of pop cans. We could have a mole of eggs. We could have a mole of shoes. Okay, a mole, like a dozen or a pair or a flat, a mole is just a number of objects. So 6.02 times 10 to the 23rd atoms is 1 mole of atoms. 6.02 times 10 to the 23rd uh, cans of pop would be a mole of pop. Okay. So a mole is just like a dozen, it's just like a flat, it's just like a pair. It's just a number, or it's just a word that has a number associated with it. Okay. So I know a mole is also a little animal that lives in the ground, a little mammal. It's also something that we sometimes see on his face. This is from the movie Austin Powers. I probably have to change this picture. You guys probably don't even know who that is. But in chemistry, a mole is neither of those things. It's not a little furry animal. It's not something that grows on your face. It's a word that's associated with a particular number of items. Okay, so a mole of atoms is 6.02 times 10 to the 23rd atoms. Like I said, a mole of peas is 6.02 times 10 to the 23rd peas. Now, how big is a mole of peas? Well, it would cover the Earth and 250 more planets the same size as the Earth, 1 meter deep. That's how big a mole is. It's a huge number. Okay, a mole of marbles, right? 6.02 times 10 to the 23rd marbles would cover the Earth to a depth of 80 kilometers. That would go out to space and more, right? If you had a mole of dollars, you could spend $1 billion every day and it would take you 1 trillion years to run out of money. Like this is a humongous amount, right? But because atoms are so small, it takes so many atoms to make up even a small amount, right? So that pencil lead earlier, there might be a mole of carbon atoms in that pencil lead, all right? And we can figure that out by using mass because a particular amount of moles of a substance has a very particular mass to it. Okay, so a mole is a group of atoms, or it's an amount of atoms or an amount of molecules. Okay, just like I said, I'm going to repeat myself over and over. Just like you have a mole of marbles or a mole of peas or a mole of eggs or whatever. It's a group of things. So where did we get this number? It's called Avogadro's number. He was a physicist, chemist, lawyer. He did it. He did it all. And in a lab, he figured out the amount of particles in a particular mass of carbon. Okay, and he came up with this number 6.02 times 10 to the 23rd particles in 12.01 grams of carbon. okay? Since there's no measuring device to measure moles, so like I said, you can't just sit there and count the number of moles, right? Because atoms are too small. Um, what we have to do is we use the mass of a mole of atoms, okay? So we know that a mole is 6.02 times 10 to the 23rd. And chemists before us have gone out and they figured out how much a mole of each element weighs. Okay. Now, why doesn't a mole of every element weigh the same? Well, because atoms are bigger or smaller, right? As you know, the larger the number on the periodic table, the more protons and neutrons it has, right? So, one atom of hydrogen, it has one proton, one neutron, one electron. Okay, but the biggest one on the periodic table, what is it? Oh, it's well, one that I can pronounce anyway. I don't know. Let's say lead. Lead, for example. Lead is number 82, right? It has 82 protons and 82 neutrons and 82 electrons. So it's much larger than hydrogen. So a mole of lead is going to weigh more than a mole of hydrogen. Okay, so the bigger the number, the bigger the number on the periodic table, the heavier that element is going to be because it's just a bigger atom. So the mass of one mole of an element is known as its atomic molar mass. Okay, now before we talked about something known as the mass number, right? We use the mass number to figure out how many neutrons something has when we know the number of protons. So the mass number and the atomic molar mass are related, but they are not the same. Okay, they are not the same, although they are related. So the atomic molar mass you're going to find on your periodic table, and it's going to be on. It's going to be in the box. Okay, and it's going to be a number that has two decimal places. Okay, so this right here is your atomic molar mass. Remember before we would round this and that would be our mass number, right? We're not using mass number anymore. Okay, that was to calculate the number of neutrons. Okay, so we're going to be using the entire number. We're not going to be rounding anything. And this number right here is what's known as the atomic molar mass. Okay, and the atomic molar mass is measured in grams per mole. Okay, so this number right here is the amount of grams, so this is grams, per mole of a substance. So if we had 6.02 times 10 to the 23rd atoms of carbon, that's a mole of carbon, that would equal 12.01 grams. Okay, so for every 12.01 grams we have of carbon, we have 1 mole of that substance. Now sulfur, again, right? Look, carbon has 6 protons and 6 neutrons. Sulfur has 16 protons and 16 neutrons. So it's obviously going to be bigger, right? So if we had 1 mole of sulfur, okay, it would weigh 32.07 grams. So 32.70 grams per mole of sulfur. Okay, so atomic molar mass is measured in grams per mole. Now, I want you guys to practice. So pause the video. You need your periodic table here. And what I want you to do is tell me, this is a gram of, or sorry, this is a mole of each of these substances. So I know by measuring out the mass of iron, right? Fe is iron. I can measure out 1 mole of iron if I know what the atomic molar mass of iron is. Okay, I can measure out 1 mole of copper. I know there's 6.02 times 10 to the 23rd molecules of copper in here because this is 1 mole of copper. How do I know it's 1 mole of copper? Because I know how much a mole of copper weighs. I know how much a mole of tin weighs. I know how much a mole of iodine weighs. So what you guys need to do is go on your periodic table right now. Okay, so pause the video, go on your periodic table, and tell me um, how much does each of these moles of these substances weigh? Okay, what's the mass of 1 mole of each of these substances? Okay, so pause it right now, take a look on your periodic table, and tell me if you could predict the mass of these containers. Okay, okay, so hopefully you paused the video. Okay, pause the video if you haven't. And what you're going to do is you're going to go on your periodic table and you're going to look at iron, Fe, it's number 26 on your periodic table, and you can see that the atomic molar mass of iron is 55.85 grams. So if you weigh out exactly 55.85 grams, we can say that there is 1 mole of atoms in there. Okay, there's 6.02 times 10 to the 23rd atoms of iron inside this container. Okay, copper, again, we take a look at copper. Its atomic molar mass is 63.55 grams. So I would have to weigh out 63.55 grams, and that tells me that there's exactly 1 mole of copper atoms in this beaker. Okay, tin is a little heavier, right? Tin is further down in your periodic table, further to the right. Okay, it's number 50 on your periodic table. So tin has an atomic molar mass of 118.71 grams per mole. So if I weigh out exactly 118.71 grams, that means I have 1 mole of tin particles inside here. And what's 1 mole of tin particles? 6.02 times 10 to the 23rd particles. Okay, that's how many atoms of tin are inside this container, right? There's 1 mole of copper in this container, which is equal to 6.02 times 10 to the 23rd, right? So again, I'm going further down the periodic table. The atoms get bigger, which mean they weigh more. So I need more of a substance to get 1 mole. Okay, so again, iodine is number 53 on your periodic table, and it has an atomic molar mass of 126.90 grams. So that means 1 mole of iodine would weigh 126.90 grams. Okay, so this is how many grams per mole of iodine. Okay, this is 55.85 grams per mole of iron, and I have 1 mole of iron in there. Okay, so that's the atomic molar mass of a substance. Now, how do we know the molar mass of compounds? So it's very easy to find the molar mass of elements because we just look on the periodic table. But as we know, elements react and they become part of molecules. And how do we know what the molar mass is of a molecule? So again, this goes back to our prerequisite knowledge, right? One of the first things I taught you in chemistry was how to write a chemical formula. So if I ask you what is the mass of a mole of sodium chloride, okay, how much does a mole of sodium chloride weigh? You would first have to be able to write out sodium chloride, right? And then from here, you can go in and you can list the numbers of atoms of each element. So I have 1 atom of sodium in that molecule. I have 1 atom of chloride in that molecule. Okay. And then what I would do is I would go on the periodic table and find the molar mass of each of these elements in the compound and add them together. Okay. And that way I can find the molar masses of compounds. Okay, so let's do that. Let's find the mass of sodium chloride. All right, so the first step that you need to take is you need to write out the formula. Okay, that's it. We'll start with an easy one. Sodium chloride. Okay, so the next thing that we need to do is we need to count the number of atoms of each element inside my compound. So I have 1 Na and I have 1 Cl. Okay, so the next thing I do is I go on my periodic table and I look at the atomic molar masses of each of these. Okay, so sodium, number 11 on your periodic table, it has a molar mass of 22.99 grams per mole. Okay, and I only have one atom of sodium in my molecule, so it would equal 22.99. Okay, chlorine, again, if I take a look on my periodic table, it's number 17. It has an atomic molar mass of 35.45. Okay, so 35.45 grams of chlorine in 1 mole of chlorine molecules. And in this particular compound, I only have one atom of that. Okay, so the chlorine weighs a total of 35.45 grams. Okay, and then after that, I just simply add them up. Okay, 4, carry the 1, 4, 1, 6, 7, 8, 3, 4, 5. Okay, so the molar mass, and molar mass is big M, the molar mass of sodium chloride is equal to 54.44 grams per mole. Okay, so if I weighed out 58.44 grams of sodium chloride of table salt, I would have 1 mole of table salt. Okay, and remember, 1 mole is equal to 6.02 times 10 to the 23rd molecules. All right, so we don't count molecules, we weigh it out, and then we figure out how many moles there is from the weight. Okay, let's try one more together, and then I am going to have you guys do a couple of practice problems. Okay, so water, H2O, there's 2 atoms of hydrogen and 1 of oxygen. Okay, so I'm going to count the number of atoms of each element I have in my compound. Okay, so hydrogen, it's the smallest of all the atoms. It has an atomic molar mass of 1.01, but there are 2 atoms per molecule, so I have to times this by 2. Okay, and this is going to equal to 2.02. Okay. Now there's only 1 oxygen, and oxygen has an atomic molar mass of 16.00. Okay, there's only 1 atom in this molecule, so it would be 16.00. Okay, so the atomic molar mass of 1 mole of water would be 18.02 grams per mole of water. Okay, so again, I could measure out 18.02 grams of water, and I know that I have a mole of water in there. Okay, 6.02 times 10 to the 23rd molecules of water in 18.02 grams. All right, so what I want you guys to do now is I want you to try the 3 molecules on page 66 of your note package. So try those right now: methane, calcium chloride, and sucrose. Okay, see if you can come up with the molar masses of those 3, and then I will go through them. So pause the video right now and try those questions yourself. Okay, so give these a try. Again, pause the video and I'll go through them individually in a minute. Okay, so hopefully you had a chance to take a look and see if you could figure out what the atomic molar masses of these compounds were. Okay, so let's start with methane. Okay, so methane is CH4, so there's 1 carbon in a methane molecule, and there are 4 hydrogens in a methane molecule. The atomic molar mass of carbon is 12.01 grams per mole, and there is 1 atom in this element. So in total, the carbon would be 12.01 grams per mole. Okay, hydrogens, there are 4 hydrogens. So hydrogen has an atomic molar mass all by itself of 1.01. Okay, there are 4 of them. So total 4 times 1.01 is 4.04. So the atomic molar mass of 1 mole of methane would be 16.05 grams per mole. Okay, perfect. Now, calcium chloride, so same kind of thing, right? We take a look, and again, sometimes in these examples I'm giving you, I believe, let me just check the notes. No, for calcium chloride, I did not give you the formula, so you would have to find the formula first, okay? So it's really important you understand how to do crisscross, right? So that we have the right prefixes, okay? So in a molecule of calcium chloride, we have 1 atom of calcium, we have 2 atoms of chlorine, okay? So 1 times calcium is 40.08, okay, grams per mole. And we have 2, so that would be 40.08, okay. And chlorine, we have the atomic molar mass for chlorine is 35.45. 35.45. Okay, 2 times 34 or 35.45. I think I don't have a calculator, but let's say I think it's 70.90. Okay, so 8, 9, 0, 11. So atomic molar mass for 1 mole of calcium chloride is 110.98 grams grams per mole. Now, what I want you guys to pay particular attention to here is significant digits. Okay, so remember when you're adding or subtracting numbers, we always go to the least amount of decimal places. Okay, so here I have 2 decimal places, here I have 2 decimal places, so my answer has 2 decimal places. Okay, you might be saying, oh, well, there's 4 significant digits here, 4 significant digits here, and there's 5 here. That's wrong. Well, no, we're adding these together. Okay, so we're adding these together, and that we stay with the amount of decimal places. Okay, well, there you go. My math was actually right. Okay, a little bit more difficult because there are a lot of molecules in here, but again, you guys get the point, right? So carbon, we would go carbon, 12.01 grams per mole for carbon, and there are 12 atoms of this, right? Hydrogen, 1.01, there are 22 hydrogens in this sucrose molecule, and oxygens, okay, oxygen is 16, where is oxygen? Is 16.00, okay, and there are 11 of these. So I would just multiply these all out and then add them up, and what I should get is 342.34 grams per mole. So to get 1 mole of sugar, you have sugar sitting on your counter or in your cupboard at home. If you measured out 342.34 grams of sugar, sucrose, you would have 1 mole of that compound of sugar. Okay, and what's a mole again? 6.02 times 10 to the 23rd molecules in a mole, right? So if you had 342.34 grams of sugar, you would have this many molecules, which is equal to a mole. All right? Okay, so I've been kind of alluding to this throughout this lecture, is that if you know how much of something you have, if you know the mass of something, you can calculate the number of moles. Um, you also need one other thing though, and you need the molar mass. Okay, so there's a formula which is the number of moles is equal to the mass divided by the molar mass. And again, you don't need to memorize these formulas. They are in your data booklets, and you would get the data booklets for any exam, right? So what we really need to know is how to use these formulas, okay? So N is equal to the number of moles, and it's measured in moles, okay, MOL. Little m, lowercase m, is equal to mass, and it's always measured in grams. So be careful. If in a question you're given milligrams, or if you're given kilograms, always convert it back to the base unit. Okay, so the base unit for mass is grams. Okay, and then big M, or uppercase M, is the molar mass, and it's measured in grams per mole. And you would get this number on your periodic table, or you would have to figure it out. Okay, but you would get these numbers from your periodic table. Okay. Okay, so let's try an example. Carbon dioxide. How many moles are in 100 grams of carbon dioxide? So this is actually, going to apply to many of the courses that you do. In Bio 30, we do a little bit of math, and in genetics, we have word problems. In math, you have word problems. Physics, chemistry, all over the place. Okay, so the most important thing to do in any of these problems is organize yourself. All right, so what they're doing is they are asking you how many moles. Okay, so what you need to do all the time is you need to put down your variables. Okay, so they're asking you how many moles. So put n is the number of moles, put a question mark. Okay, what are they telling you? So first of all, what are they asking you? Second of all, what are they telling you? They're telling you the mass. Okay, they're telling you that you have a mass of 100 grams of carbon dioxide. Okay, now we know that the formula is N equals M divided by big M, right? So to find the number of moles, we need mass and we need the molar mass. So we're missing something here as well. We're missing the molar mass. Okay. Now, generally in a question, you can't answer it if you don't, if you have multiple variables that you don't know, multiple unknowns. But in this case, we can figure out what the molar mass of carbon dioxide is, right? We know that carbon dioxide has one carbon in it, and carbon has a molar mass of 12.01 grams per mole. Okay, and there's only one of them, and we know that carbon dioxide is CO2, right? So we have to write out our formula. Okay, and we know that there are two oxygens, and oxygen is 16.00, okay, times 2, right? There's only one carbon. So we can calculate the molar mass of our carbon dioxide, okay, as we were doing in our last examples. Okay, so we know that the molar mass of carbon dioxide is 44.01 grams per mole. Okay, so now we have what we are being asked in the question, and we have what we're being given in the question. We have our formula on how to answer it. Okay, and then basically now we just plug in the numbers. So N is equal to the mass, which is 100 grams, okay, divided by the molar mass, which is 44.01 grams per mole. Okay, the grams are going to cancel out here, and we are going to get, hold on, I just need to pull up my calculator. 100 grams divided by 44.01 grams per mole. We are going to get a big number, 2.27221, on and on and on, okay, moles. Now, this is where I have to go back and look at my significant digits. So here I have 3 significant digits. Here I have 4 significant digits, Because I'm dividing, I use the least amount of significant digits, which is 3. So the number of moles is going to be equal to 2.27 moles. Okay, so in 100 grams of carbon dioxide, I have 2.27 moles of carbon dioxide molecules. All right, so a question like this is going to be worth 3 marks. I would give you 1 mark for your variables. I would give you 1 mark for your formula, and I would give you 1 mark for the answer with the correct units and the correct number of significant digits. Okay, so this would be out of 3, 3 out of 3. Let's try another one. How many moles of zinc chloride are in 56.1 gram sample? Okay, so again, how many moles? Okay, they're telling us the mass of the zinc chloride is 56.18 grams. Now, zinc chloride, I have to go in and figure this out. Okay, zinc, Zn. Zn has a charge of, zinc, zinc. Okay, zinc has a charge of 2 plus. Chloride has a charge of 1 negative. So I have to crisscross. Okay, so Zn, zinc chloride would be ZnCl2. Okay, that's my formula, ZnCl2. Okay, so then now I have to figure out what my molar mass is. So my molar mass, I have one zinc atom in there, and zinc is 65.41. Okay, and times 1, because I only have one of them. Okay, and my chlorine atoms in zinc chloride, I have 2 of them. Okay, so chloride is 35.45. Okay, but I have 2 of them in my zinc chloride, so that would be equal to 70.90. Okay, so the molar mass of zinc chloride would be 65.41 plus 70.90. Okay, gives me a molar mass of 136.31 grams per mole. Okay, so I have all my variables. Okay, next I write my formula. N is equal to, number of moles is equal to the mass divided by the molar mass. Okay, and then I just plug my numbers in. 56.18 grams divided by 136.31 grams per mole. Grams cancel out. 56.18 divided by 136.31 gives us the number of moles. It's equal to 0.4121 moles. Okay, so I want to make sure that I have the right significant digits. So I have 4 here, I have 5 here. So my answer has 4. I have the units. Excellent. Okay, so 1 there, 1 there, 1 there. 3 out of 3. Okay, last one. Let's try another one here. So again, calculate the number of moles of beryllium nitride. Okay, so what are they asking me for? Number of moles. What are they giving me? Giving me the mass, 250.0 grams. Make sure that you write out all the numbers, right? Because that's 4 significant digits here now. Okay, and that might become important later. And I need to figure out my molar mass. Okay, so beryllium nitride. Okay, beryllium, Br, beryllium, or just, sorry, no, it's not Br, it's Be. So beryllium 9.01. Okay, so beryllium going to have a molar mass of 9.01. But how many berylliums are there? Okay, beryllium has a charge of +2. Okay, so beryllium is Be2 plus. Nitride is 3 negative. Okay, so we crisscross and we come up with Be3N2. Okay, beryllium nitride. So there are 3 berylliums, so 9.01 times 3, okay, that would be 27.03, okay, and then there are, nitride is 14.01, there are 2 nitrides, this would be 28.02, add them together, 5055. Okay, so my molar mass of beryllium nitride would be 55.05 grams per mole. Okay, the next thing I want to do is just plug these numbers into my formula. Okay, so the number of moles is equal to the mass, 250.0 grams, divided by the molar mass of beryllium nitride. We figured that out to be 55.05 grams per mole. Okay, plug that into my calculator. 250 divided by 55.05. Okay, gives me again a big long number, but I look at my significant digits. I have 4 sig digs here. I have 4 sig digs here. So the number of moles is equal to 4.541 moles. Okay, so there's 4.541 moles of beryllium nitride in 250 grams. Okay, so 1 mark here, 1 mark here, and 1 mark here. Okay, I guess I should write out the formula, N equals mass divided by molar mass. Okay, so a few steps there. What I'm really going to be looking for is how you organize yourself. So make sure that you write out all your variables, what you're given and what you're asked. You write out your formula. Okay, you plug your numbers into your formula, and then you write out your answer with the correct amount of sig digs and the correct unit. Okay, so we can mess around with this formula depending on what information we're given in the question. Okay, so you can also use this formula to also find mass, okay, and molar mass. But how can we do this? Well, we have to have a different number of variables. So we can find mass if we know the number of moles and if we know the molar mass. And we can always calculate the molar mass if we know the formula, right? So using the formula to find the mass requires us to rearrange the formula. And we worked on this at the beginning of the year. I don't know if you guys remember, in our science skills, we talked about how to rearrange formulas to solve for mass. Okay, so mass is equal to number of moles times the molar mass, right? So remember our original formula was N is equal to mass divided by molar mass. All right, how do we get mass all by itself here? Well, because we're dividing by molar mass, if we multiply by molar mass over here, we cancel out. We multiply by molar mass over here. Now we're left with mass all by itself. Now, word of warning, you're given the original formula in your data sheet, but you have to know how to manipulate the formula. Okay? All right, so let's organize ourselves. In this question, they're asking us, what is the mass? So my mass has a question mark. What are they telling me? They're telling me that I have 10 moles of the stuff. Okay, now we're dealing with water. Water is H2O. Okay, so I can find my molar mass. So the molar mass is H 1.01. There's 2 of them times 2. 2.02. Okay, oxygen is 16.00. There's only one of them. After a while, you start to get to know some of the masses of some of these common chemicals, right? So 2, 0, 18. So the molar mass of water is 18.02 grams per mole. All right, so how much does 10 moles of water weigh? Well, mass is equal to the number of moles times the molar mass. Okay, so mass is equal to 10.0 moles times 18.02 grams per mole. Now moles cancel out here and I'm left with grams, right? Okay, so the mass of 10 moles of water is going to be 180.2 grams. Now, am I okay with this? Well, if I look back here, this is 3 sig digs. Okay, over here I have 4 sig digs. So my answer can only have 3 sig digs, so I'm going to just round it. So the mass of 10 moles of water is 180 grams. Okay. Okay, so let's try one more here. What is the mass of 5 moles of sodium hydroxide? So again, I'm going to list what they're giving me. They're telling me the number of moles, 5.0 moles. Okay, they're asking me for mass, and I can figure out my molar mass. So again, Na, there's one molecule of Na, or atom, sorry. There's one atom of oxygen, and there's one atom of hydrogen. So hydrogen, 1.01, oxygen, 16.0100, and sodium, I don't know that one off by heart. Sodium, 22.99. Okay, and these are all times 1, times 1, times 1, because there's only one of them. All right, so if I add them all up together, again, I'm going to use my calculator, make sure I don't make any mistakes. 22.99 plus 16.00 plus 1.01 gives us a total atomic molar mass for sodium hydroxide of 40.00 grams per mole. Now, some of you might have been doing this with your calculator and you just got 40. Okay, it adds up to a nice whole number. Why did I add the 00? Because again, remember, I'm dealing with decimal places when I'm adding these numbers. Okay, so I have to add 2 decimal places. This tells me, the degree of certainty in my measurement. Remember way back, right, to measuring. So now I have my variables. Next thing I have to do is figure out my equation. Okay, my equation is mass is equal to number of moles times molar mass. Number of moles, 5.0 moles. Okay, divided by molar mass, which is 40.00 grams per mole. Moles cancel off. Okay, and I'm left with a mass of 200.00 grams. Okay, now I have to take a look at my formula here. I only have 2 significant digits here, and I have 4 significant digits here, and my answer has way too many significant digits, right? So I have to have the least amount of significant digits. So what I'm going to do is I'm going to convert this into scientific notation. So I'm going to move my decimal 1, 2 places. So it becomes 2.0 times 10 to the 2 grams. Okay, so now remember when I'm counting significant digits of scientific notation, I just count these. All right, so now I have the correct amount of significant digits. Put a little square around your answer. 1 mark here, 1 mark here, 1 mark here. Okay, so If I would have just put sodium hydroxide here, you would have had to come up with the formula. Okay, so there's a place you can make a mistake. Then I have to figure out my molar mass. It's another place you can make a mistake, right? I have to manipulate a formula. Again, I can make a mistake. Then I can have to plug all this into my calculator. Okay, and then I have to figure out the amount of significant digits. So there are a lot of places to make mistakes. That's why we have to really organize ourselves. Okay, so let's try another practice problem here. What is the mass of 4.3 moles of ammonia? So they're asking us for mass, giving us the number of moles. Okay, 4.3. And we need to figure out the molar mass. Okay, so nitrogen, and we have hydrogen in ammonia. Okay, 1.01, and there are 3 of these. Okay, so this would become 3.03. Then nitrogen, has a molar mass of 14.01. There's only one of them, so 14.01. Add them together, 40. Okay, so ammonia has a molar mass of 17.04 grams per mole. Mass is equal to the number of moles times the molar mass. Mass is equal to 4.3 moles multiply by 17.04 grams per mole. Okay, the moles cancel off. 4.3 times 17.04 gives us a mass of 73.272. Okay, so again, I'm in the kind of the same boat here. I have a big number. This has 2 sig digs. Okay, and this has 4. So my answer can only have 2. So the mass is equal to 73 grams. Now, if you would have moved the decimal place here and put 7.3 times 10 to the 1 grams, would you be wrong? No, either of these is correct. Okay, this is just less work. And you guys know Forrest J's motto, right? Work smart, not hard. All right. But again, you could definitely do this if you want to get into that habit, and you would be fine as long as there are 2 significant digits. So as I mentioned, question when you're asked to find the number of moles or you're asked to find the mass will be typically worth 3 marks. Okay. Now in your note package, it's different than what I have on this slide. Okay. So please correct your note package. Again, your note package is incorrect with these 3 bullets. Please correct your note package. Okay, so how am I going to mark you on this? Number 1, you get 1 mark for writing the formula that you're using. All right, so whether it's N is equal to mass over molar mass, or it's mass is equal to N times N. Okay, so write the formula that you use. And this is going to go for physics as well. Okay, we're going to review this again in physics, but you're going to get the same 3 marks. So write the correct formula. You get 1 mark for listing your variables and your unknowns. Okay, so this is different than your note package, so please correct that. All right, so as I said, you get 1 mark for listing your variables and your unknown. You get 1 mark for writing the formula that you're using, and you get 1 mark for the correct answer with significant digits and units. So, you could mess up in your calculator and still get 2 out of 3. You could be messy and get the right answer, but you'll only get 1 out of 3 if you don't do the other 2 things. All right, so 3 marks for a question like this. 1, correct variables and your unknown. And again, you'd lose a mark here if you didn't do your molar mass right, but then you'd screw up your answer as well, right? So writing your formula of the chemical that you're dealing with, really important. Getting your molar mass, all right, putting it down, that's your variable. A mark for writing the formula, and again, you might have to manipulate that formula, and then the correct answer was sig digs. Okay. Now, we talked about Lavoisier and his law of conservation of mass, and we can actually use these formulas to prove his law. Okay, so we can mathematically prove his conceptual law. Okay, and basically what he said is you cannot create or destroy matter, and what you start with is what you have to end up with. Okay, so let's take a simple equation. We'll balance it. Okay, the coefficients tell us what the number of moles are, right? So this is important. Highlight this in your notes, please. The coefficient is equal to the number of moles of that substance, all right? So if we're given a balanced chemical equation, we can, those are the number of moles of those particular chemicals that are being used to make a total balanced equation. And again, you're going to use this in Chem 20 in something known as stoichiometry. Okay, so this is a really important concept. All right, so if we take a simple reaction, a simple composition reaction, where we take sodium metal and burn it in the presence of oxygen. This is not a hydrocarbon combustion. Sodium is not a hydrocarbon, but this is just a formation reaction. Okay, so basically it's rusting, right? If we did this with iron, it would be rusting. This is sodium. It's much more spectacular. I showed you a video of what happens when sodium reacts with oxygen, right? We had big flames and and we get sodium oxide. Okay, so basically this chemical formula, it's balanced. It tells us that 4 moles of sodium are required to react with not 0 moles, 1 mole of oxygen, right? And this gives us 2 moles of sodium oxide. Okay, so if we look at the balanced chemical equation for this, we can actually prove that we don't create or destroy mass. Okay, the law of conservation of mass is intact here. Let's take a look. Let's divide our formula into products versus reactants. So our products are on the right hand side, our reactants are on the left hand side. Okay, so let's determine the mass of our reactants. Okay, so first of all, we have 4 sodium atoms, okay, or 4 moles of sodium atoms, I should say, 4 moles, because the coefficient is equal to the number of moles, okay? So I have 4 moles of sodium, and the molar mass for sodium is equal to, where is it? 22.99, okay, 22.99 grams per mole, okay? And right here, I have moles of sodium. Okay, so how many grams of sodium do I have on this side? Well, remember, to figure out mass, I take my number of moles times my molar mass. So the mass of sodium on this side here would be 4 times 22.99, okay, gives us a mass of sodium of 91.96 grams of sodium. Okay, now of oxygen, I have 1 mole of oxygen, but I have 2 oxygen atoms, right? So this would be 2 times 16.00, okay, which gives us a molar mass of 32.0 grams per mole, okay, right? And the number of moles that I have is 1, okay? So my mass is equal to the number of moles, 1 times the molar mass, which is 32.00 grams per mole, okay, which gives us a mass of 32.00 grams of oxygen, okay, of oxygen. So if I added these two together, I get a total mass of my reactants Okay, so the reactant mass is equal to 123.96 grams. Okay, so that includes the mass of my oxygen and that includes the mass of my sodium. Okay, so in total, my reactants make up 123.96 grams. Okay, now if I look over here, how many moles of sodium do I have? Well, I have 2 moles of sodium oxide, but there are 2 atoms per, per mole. So I would have to go 2 times 2. Okay, so that's a total of 4 moles of sodium atoms, right? Which is, we calculated that already. Okay. But let's do it again. My sodium is 22.99. Okay, so my molar mass of 4 moles of sodium, okay, which would be 4 times 22.99 is equal to 91.96, okay, grams per mole, right? No, sorry, grams, because the moles got canceled out in our formula. And then how much oxygen do I have? Well, again, this 2 applies to this oxygen as well. So I have 2 moles of oxygen. Okay, so 2 times 16.00 gives us a total of 32.00 grams of oxygen. And if I add these two together, I get 123.96 grams of sodium oxide, right? So what I see is that on each side of my reactant and product side, I have the same mass, right? Even though over here on my reactant side, I have this lump of grayish metal and I have this colorless gas. When I apply some energy to them, they form into this kind of powdery substance. But if I were to weigh this and I were to weigh these two things, what I would come up with is the same mass, 123.96 grams of sodium and oxygen, and then I get 123.96 grams of sodium oxide. Okay, so Lavoisier's law of conservation of mass is proven here. And you can do this with any chemical formula. Okay. All right, so what I would like you guys to do now is I would like you to work on pages 70 and 71 of your note package. Okay. Yeah, if you have any questions, you can take a look at the key on the Google site, not the Google Classroom, but the Google site. Take a look. And if you really can't get anything, by all means, you can email me, okay? And either we can chat through Microsoft Teams, or we can chat on the phone, or we can just chat on email. If I get enough of the same question, I'll record a video and I will post it up on the Google Classroom and I'll go over the homework. Okay, take care. I'll talk to you again through this format in a few days, next week, whenever. Okay, so keep tuned into the Google Classroom for any updates. Okay, have a great day.